study of the gas laws, in particular Gay-Lussac'S pressure law, and here we have pictures of the Breitling orbiter, which was the first balloon to circumnavigate the globe non-stop in 1999. And with the gas laws, you're investigating relationships between pressure, volume, and temperature, and we look at two of those at any one time and keep the other one constant. And what are we going to keep constant in Gay-Lussac'S pressure law? So the number of moles, which is the same for Charles and Boyle's as well, but this time we're going to keep the volume constant. So we're going to investigate the relationship between temperature and pressure of a gas, going to keep V, the volume, constant, and N, the number of moles, constant. So we need an apparatus that keeps the volume of the gas constant, but allows the gas to be heated and its pressure measured. So pause here, put down your ideas, draw what you think might work. So pause. Here's one idea, round bottom flask with a pressure gauge on top and a water bath or a beaker with water and a Bunsen burner to heat the water. Safety, as with any experiment, goggles, apron, lab coat, care with the heat and glassware, and in particular here with pressurized gases. So in this experiment, you're not heating the water in the water bath to more than 75 degrees Celsius. So you're going to record the experimental data that's given, or if you're doing the experiment, the actual measurements that you have. Here is a possible data table, and for the one that you're looking at the data here, put the pressure in, because very hard to get small changes in pressure from the diagram that I've given, but pause each time to get the temperature of each trial as you are going through them. So the first one, which is the temperature and pressure of the room, and look at the pressure scale and the value that I gave as well, and pause until you've got the temperature and go on to the next one. And here's trial 2, again pause, and trial 3, different temperature, read it carefully. Trial 4, pause to get the temperature. Trial 5, trial 6, and the last one for trial 7. And then we're going to analyze the data, but first look at your data table. Do you see any trends? How are the temperature and pressures changing in relation to each other? We're going to analyze the data with a graph, but plotting the graph in a slightly different way, just going to use the top right-hand quarter graph paper. You're going to plot pressure against temperature in degrees Celsius, just in that top quarter of the graph paper. Temperature on the horizontal axis. So predict what you think the shape of the graph might be, and then as you draw it, you're going to analyze what it gives you. So plot carefully. If it's a straight line, you've got a mathematical relationship. If it goes through the origin, x, which was temperature, is directly proportional to y, but ours doesn't. But what we can do with our line is we can extrapolate it, extend it backwards, so it goes through the x-axis, and that will be the value of absolute zero. So you're extending it backwards, and then looking at the scale, degrees Celsius, you can find the value in degrees Celsius, obviously below zero, which will be equal to 0 Kelvin. And so we've got a straight line graph, and pressure is proportional to the absolute temperature, provided the volume and the number of moles are kept constant. And here are some other pressure scales, bar, kilopascals, millimeters of mercury, also inches of mercury as well. 1 atmosphere is about 29.3 inches of mercury. And look at the top one, conversion, 1 atmosphere is 101.325 kilopascals. And there's a conversion example below, 3.52 atmospheres. So start that in the dimensional analysis box at the end, then put your conversion factor with the denominator being the atmospheres, because you're going to cancel those and do the numerical calculation. So we end up with 357 kilopascals. So that's what that fourth column was for, converting atmosphere's pressure to kilopascals. So for each of the trials, convert the pressure to kilopascals. You might need to just go back in the video to get help with that and the conversion factor as well. So in the experiment, what are experimental errors? And how could you improve your data collection, reducing the experimental errors without introducing any others? So pause the video whilst you're thinking about that one. And then in words, the pressure of a fixed mass of gas, same number of moles, directly proportional to the absolute temperature, providing the volume remains the same. And then we can look in terms of mathematical relationships. Pressure is directly proportional to temperature, and that can be written as P equals KT, where K is a constant and it's the slope of the graph. So for the first trial, P1 equals KT1, and for the second trial, P2 equals K2, etc. And so we can then rearrange both of those in terms of K, so that P1 over T1 and P2 over T2 equals K. So they equal each other, which is our representation of GAY-LUSSAC'S law. And then we're going to apply it in a calculation. So we've got a scuba tank containing compressed air at 200 atmospheres. What will its pressure be at 150 degrees Celsius when it was originally at 25 degrees Celsius? Do not heat any contained cylinders, just so dangerous. We're assuming the volume doesn't change, so you're going to ignore any expansion of the container that might occur, and assume the same number of moles. Now, for these calculations, every time define each of the variables with their units and write down the law that you are using. So we're defining P1, P2, T2, and T2. P2 is our unknown with the question mark. And we're going to use GAY-LUSSAC'S law, P1 over T1 equals P2 over T2, substitute in the values and do the calculation. So we get an answer of 284 atmospheres. Now, does that seem what it should be? So always look at your answer, go back at the question. Is that what it should be? And then we're going to look applications in everyday life, autoclaves and pressure cookers. Diagram on the right is an autoclave, and high temperature, higher pressure to sterilize metallic surgical instruments and to sterilize medical waste. And you get temperatures over 120 degrees C for at least 15 minutes. And the pressure is double room pressure. And for the pressure cooker diagram on the left, you're raising the pressure, which is increasing the boiling point of water. In an open saucepan, it's 100 degrees Celsius, but under pressure, you'll get the cooking temperature 120 degrees Celsius. Best for longer cooking items because it takes time to get the food up to, in the pressure cooker, up to high pressure, high temperature, and it takes time to release that pressure as well. We're just going to look at a different method of measuring pressure, which is a manometer. It's simply a U-tube, and if you've got the same pressure on either side, the levels are going to be equal. And in our experiment, you start with the equipment separated. You've got one room pressure in the flask, and the levels in the U-tube limbs are equal. When you connect them, they stay that way at the room conditions. As you start heating, you're getting increased pressure in the flask, and so on the left-hand limb of the U-tube. So explain in kinetic molecular theory why pressure increases when gas is heated. On the right-hand side, you've still got the open limb, and the pressure around that is the pressure of the atmosphere. So the difference, the pressure of the gas, is atmospheric pressure plus that H. Now, in previous times, it used to be a mercury manometer. So you could easily measure even relatively slight differences in pressure. With water, the U-tube would have to be so large. So we're just doing it qualitatively here. And then we can just look at a bit more about Gay-Lussac's life. So pause this to read it. As with other contemporaneous scientists who are working with gas laws, they actually used balloons to do investigations. Gay-Lussac also was a co-discoverer of the element boron with Thénard and did empirical formula calculations with cyanogen. An unfortunate application of Gay-Lussac's law is that car tires explode. The air in the car tire is already under pressure, fixed amount of material. And as the temperature rises, so does the pressure, and eventually the tires can explode. And then there is a further law that Gay-Lussac developed. And what he was saying is, when gases react, they do so in volumes that bear a simple whole number ratio to each other and to the volume of the product if it is a gas. So what we're doing here is looking initially at Avogadro's law with the number of moles from the equation nitrogen and hydrogen giving ammonia, and the number of moles being proportional to each of the volumes. For the first one, I'm doing that one for you as an example. The ratios of nitrogen to hydrogen, looking at the coefficients 1 to 3. So for the volumes 1 to 3, 5 milliliters of nitrogen, 15 milliliters of hydrogen. And the ratio of the volumes of nitrogen to ammonia, 1 to 2 for number of moles of both of those chemicals. So 5 milliliters of nitrogen will give 10 milliliters of ammonia, provided it's under the same conditions of temperature and pressure. And it only works for gases. So you can do parts 2 and 3, you can pause it there. And finally, some animations that might interest you, because you can actually see the particles and what happens as you change different items. And our next item will be to look at the ideal gas equation.